Welcome back. This is Stage 2, Lesson 8, and today we're revisiting Layer 2. Even if you remember switches forwarding frames by MAC address, there's a lot more going on under the hood. Over the next few minutes, we'll dig into the three core mechanics every switch relies on: learning, flooding, and aging, plus the MAC table that ties them all together. Here's the roadmap for the next few minutes. First, we'll look at how a switch actually builds its MAC address table, not in theory, but observing the process frame by frame. Then, we'll walk through the forwarding decisions a switch makes for unicast, broadcast, and that interesting case of unknown unicast. From there, we'll tie together learning, aging, and flooding, the three mechanics that drive everything at Layer 2. And finish by cracking open an Ethernet frame to see exactly what the switch is reading. Let's actually crack open that frame before we go any further, because everything a switch does revolves around these bytes. After the preamble synchronizes the receiver, the very first meaningful field is the destination MAC, 6 bytes that tell the switch where to send this frame. Then comes the source MAC, which is how the switch learns who lives on which port, the ether type identifying the Layer 3 protocol inside, the payload itself, and finally the FCS, a CRC32 checksum. If that checksum fails, the frame is silently dropped. No retransmission here. Recovery is TCP's problem, not Ethernet's. Now that destination MAC isn't just a random number, it has structure. 48 bits, split right down the middle. The first 3 bytes are the OUI, the Organizational Unique Identifier, handed out by the IEE to each vendor. So 001B21 tells you immediately that's an Intel NSA. 0050.56 is VMware, which is a dead giveaway. You're looking at a virtual machine. The last 3 bytes are the vendor's serial, burned into ROM at the factory, giving roughly 16.7 million addresses per OUI. And yes, that whole address can be overridden in software, which is what we call MAC spoofing. So with addresses in hand, how does a switch actually learn who's where? It watches the source MAC of every frame that arrives and notes which port it came in on. Here, host. A sends a frame from A into port 1. The switch instantly records that pairing in its MAC table and starts an age timer at 0. That's the entire learning rule. Source MAC plus ingress port written down on every frame received. Notice it learns from the source, never the destination. The destination is what it has to figure out next. Once the switch knows the source, it turns to the destination MAC to decide what to do. And there are really just 3 cases. If the destination is already in the table, it's a known unicast, and the frame goes out one single port, nice and surgical. If the destination isn't in the table yet, it's an unknown unicast, so the switch floods it out every port except the one it came in on, hoping the reply will teach it where that host lives. And if the destination is the all-ones broadcast address, like an ARP request, it always floods. No lookup needed. There's even a quiet 4th case. If a frame is somehow addressed back to its own ingress port, the switch just drops it. Let's walk through that unknown unicast case in slow motion. Host A sends a frame to host C. The switch immediately learns that AA lives on port 1, but C is nowhere in its table, so it's flagged unknown. With no other option, the switch floods the frame out ports 2, 3, and 4, every port except the one it arrived on. When host C eventually replies, that return frame carries CC as its source, and the switch finally pins CC to port 3. From this moment on, traffic between A and C is pure unicast. The flood was just the cost of learning. Now, learning would be useless if those entries stuck around forever. That's where aging comes in. Every time a switch creates a MAC entry, it starts a timer. On Cisco gear, that's 300 seconds by default. 5 minutes. Each new frame from that MAC resets the clock. But if the device switch hears nothing for the full 5 minutes, the entry gets quietly removed. Why? Because devices move. A laptop unplugged from port 4 and replugged into port 9 shouldn't be chased down the old path. Hosts power off. topologies change, and stale entries just waste precious table memory. Now let's clear up two terms that constantly trip people up: collision domains and broadcast domains. A collision domain is a group of hosts fighting for the same physical wire. Back in the hub days, every port shared one, which was painful. Modern switches give each port its own collision domain, and with full duplex Ethernet, collisions simply can't happen anymore. A broadcast domain, on the other hand, is the set of hosts that hear each other's broadcast frames, and by default, an entire switch is one big broadcast domain. The bigger that domain grows, the more ARP requests and background chatter every host has to process, which is exactly why VLANs exist, and that's where we're headed next. Before we dive into VLANs, let's get our hands on the actual commands you'll use on a Cisco switch to inspect everything we've talked about. Show MAC address table is your window into the learning process. You'll see each MAC, which VLAN it belongs to, and the port it was learned on. Show MAC address table count tells you how full the table is, which matters on busy switches. You can tune the aging timer from its default of 300 seconds, and when you're troubleshooting a weird forwarding issue, clearing the dynamic entries forces the switch to relearn everything from scratch, often a quick fix. Now, when things go wrong at layer 2, the symptoms tend to repeat across networks. MAC flapping, the same address bouncing between ports, almost always means you've got a loop, and the switch is seeing the same frames arrive from two directions. Unicast flooding is subtler. If your MAC aging timer expires before ARP refreshes, the switch forgets the destination and floods every frame. A broadcast storm is the critical one. A loop without spanning tree will pin your CPU at 100% in seconds. Cam table exhaustion usually points to an attack, and a wrong VLAN assignment is the classic "it's plugged in but can't ping anything" config mistake. So let's lock in what really matters from this lesson. A switch learns by reading the source MAC and the port it came in on. That's the entire foundation. Anything it doesn't recognize, plus every broadcast, gets flooded out all ports except where it arrived. The aging timer, 5 minutes by default, quietly cleans house so the table reflects reality. And remember the domain rule. Every port is its own collision domain, but the whole switch shares one broadcast domain. And that's exactly the limitation VLANs are about to solve in our next lesson. Here's your one-page reference for everything we covered. Keep this close: the frame structure, the MAC address, breakdown into vendor and device portions, the 3 forwarding behaviors for known unicast, unknown unicast, and broadcast, plus the aging timer and the domain rules. And don't forget the command at the bottom, show MAC address table. That's how you actually see this learning process happening live on a real switch. And that brings us to the end of Lesson 8. Next up, we take everything you just learned about Layer 2 and split it apart, literally. Lesson 9 is all about VLANs, how a single physical switch can host multiple, completely isolated networks at the same time, and why that segmentation is one of the most powerful tools in your switching toolkit. I'll see you in the next one.